Okay, this is section 8.3, exercise number 24, in which we're asked to use the limit comparison test to determine convergence or divergence of the given series. So we need to come up with a candidate to compare our series to, and again, we have an exponential and a polynomial term, in this case quadratic, in the denominator, and we know, again, from experience, that the exponential term is what tends to dominate the behavior or explain the behavior. So we're going to compare to simply 1 over 4 to the n. So the limit comparison test says let's look at the ratio of these two terms, and the limit then as n goes to infinity of that ratio. So we want to look at the limit as n goes to infinity of the ratio 1 over 4 to the n over 1 over 4 to the n minus n squared. So we have a little bit of algebra to do to clean up this expression. This is 4 to the n minus n squared over 4 to the n. And if we want, we can separate that into 1 minus n squared over 4 to the n. We could stop here. This second expression, again, we have a polynomial on top and an exponential on the bottom, quadratic over an exponential. The exponential is going to dominate as n goes to infinity. And so we're going to have a term here leading to 0. If you weren't quite sure that that was leading to 0, technically as n goes to infinity, this has an indeterminate form of infinity over infinity. And a couple of applications of L'Hopital's rule will show you that that derivative is in fact going to 0. And so this limit is simply 1. We're left with the 1 term here. If we look at theorem 8.3.3, which is our limit comparison test, in particular the first part, the fact that our limit is equal to 1 tells us that the two series have the same either convergent or divergent behavior. So since the series 1 over 4 to the n converges, so ours does too. They have the same convergent or divergent behavior if the limit is equal to a finite positive value. And so since the geometric series converges, our series converges too.